Welcome to This Explainer. Today, we are diving into the fascinating physics behind nature's most ubiquitous and, let's be honest, beautiful illusion. It's something we literally see all the time, yet rarely pause to truly understand. So let's unpack exactly what is happening right above our heads. Think about it. Every single day you step outside on a clear day, boom, there it is. This massive, vast dome stretching endlessly above you. But why is it specifically blue, right? Why not a vibrant green, a deep red, or, I don't know, a bright purple? It's something so common we just kind of accept it. But let's ask the obvious question and actually figure out what's really going on up there. Okay, to solve this mystery, we've got to start at the source. We need to track a single beam of sunlight as it leaves the sun and hurtles towards Earth. Sunlight is absolutely our primary suspect here, and understanding its true nature is step number one to unlocking the secret of the sky. I mean, it seems simple enough when it's warming your face on a sunny day, but that light, it's hiding a massive secret. See, even though sunlight looks perfectly white to our naked eyes, it's actually this incredibly rich, densely packed mixture of the entire color spectrum. Think of a rainbow. You've got violet, indigo, blue, green, yellow, orange, and red. Every single one of these distinct colors is just hitching a ride inside that one beam of seemingly white light, zipping across the vacuum of space. Now here's where it gets really interesting. These colors aren't just visually different to us. They physically possess completely different wavelengths. On one end of the spectrum, you have these short, tightly packed, energetic wavelengths. That's your blues and violets. And then on the exact opposite side, stretching out, you've got these long, lazy wavelengths, your reds and oranges. You're going to want to keep this physical difference in mind because it is the absolute key to this whole illusion. So, as our beam of sunlight finally reaches Earth, it doesn't just hit the ground free and clear. No way. It slams into what is essentially a giant atmospheric obstacle course. High up there, the sky is absolutely loaded with gas molecules, mostly nitrogen and oxygen, plus all this suspended dust and microscopic water droplets. Our light literally has to navigate all this invisible clutter before it ever even reaches our eyes. And this massive microscopic collision creates a phenomenon called Rayleigh scattering. Simply put, when sunlight hits these tiny molecules, a fierce battle of physics kicks off. The light with the shorter wavelengths, remember those tightly packed blues and violets, they get knocked completely off course. They get scattered so much more strongly, bouncing in all directions, while those longer, lazy red wavelengths kind of just power straight through the clutter. Now, there is a strict mathematical reality at play here. Scattering intensity is inversely proportional to the fourth power of the wavelength. But hey, you don't need to be a physicist to grasp how cool this is. It basically boils down to one strict rule. The shorter the wavelength, the more violently and frequently the light gets bounced around by the gases in our atmosphere. It's literally like a chaotic game of pinball happening at a microscopic scale. And because of that specific math, the results are wild. Blue light, with its tightly packed short wavelengths, actually scatters about 10 times more than red light. 10 times! It gets completely dispersed, just ping-ponging off oxygen and nitrogen molecules over and over and over again, totally saturating the entire sky above us with that signature blue glow. To really picture this in your head, imagine you're shining a bright white flashlight into a totally dark, super foggy room. The fog acts exactly like our atmosphere, right? It spreads the light from the beam everywhere. But because of how the light interacts with those tiny fog particles, the blue light scatters the absolute easiest, tinting the whole room this eerie bluish hue. That exact same dynamic is happening miles above your head right now. Okay, but wait, let's look at a pretty massive plot twist. Since violet light has an even shorter wavelength than blue light, shouldn't it scatter even more? I mean, if we're following the strict rules of Rayleigh scattering we just talked about, shouldn't we be looking up at a vibrant, deeply purple sky every single afternoon? It's a great question. We solved this little sub-mystery by looking at three specific culprits. First, the sun itself. It turns out there's just less violet light in sunlight to begin with, so we're already starting at a deficit. Second, our upper atmosphere acts like this giant protective filter, actually absorbing a good chunk of that violet light before it ever gets down to us. And third, well, it comes down to biology. Human eyes are just naturally wired to be way more sensitive to blue light than to violet. And this brilliantly illustrates why, despite the super aggressive scattering of violet light up there, we ultimately process the sky as a brilliant blue. It's this perfect, really delicate harmony between the sun's raw material, the atmosphere's physical filtering process, and the literal biological wiring inside our own eyes. So this naturally leads us to another everyday miracle. If the sky is so reliably blue during the day, why in the world does it dramatically transform into this huge canvas of fire, rich reds, oranges, and yellows when the sun goes down? It almost feels like the rules of physics suddenly change, right? But actually, scratch that, they're just acting on a brand new set of variables. It totally comes down to the geometry of the light's journey. During a sunset, the sun is way low on the horizon. That means the light has to travel a much, much longer horizontal path through the absolute thickest part of the Earth's atmosphere. Just compare that to midday, where the sun is directly overhead, and the sunlight takes this super short direct path straight down to you. Because that sunset path is just so incredibly long, almost all of that highly scatterable blue light is completely dispersed and bounced away way before it ever reaches you. It literally gets filtered out by the sheer distance. So what remains? Only the long wavelength colors, the reds, the oranges, and the yellows. They are literally the only ones capable of surviving that grueling journey through the atmospheric obstacle course to completely dominate the horizon at dusk. To truly appreciate the mechanics of our own planet, let's zoom out for a second to a cosmic perspective. A planet's specific atmosphere completely dictates the color of its sky. The blue we see, it's not some universal given across the galaxy. It is a very local, earthly phenomenon born completely from our unique chemistry. Just looking at our cosmic neighbors shows exactly how special our home is. Our unique nitrogen and oxygen mix gives us that gorgeous deep blue. But jump over to Mars, and its heavily dusty atmosphere scatters light completely differently, giving you this reddish, hazy sky. And the moon? Well, because it totally lacks a thick atmosphere to scatter light in the first place, its sky is a pitch-black void, even in broad daylight right next to the blazing sun. Crazy, right? So let's quickly recap the remarkable journey of our little photon. It starts out as this full, rich spectrum of colors inside white sunlight. Then it hits our atmospheric obstacle course. Thanks to Rayleigh scattering, the shorter wavelengths totally win the scattering battle. And finally, our blue-sensitive eyes catch that perfectly scattered light reaching us from every single direction, completing the whole picture. Ultimately, what you should really take away from this explainer is that the sky isn't just some static ceiling or painted dome above us. It is a live, continuous optical illusion. It's a real-time demonstration of light colliding with matter in the most elegant way possible, and it is happening constantly, right above our head. So the very next time you step outside on a beautiful, clear day and look up, take a moment to actually appreciate the science happening up there, and ask yourself, if the entire sky is just a brilliant illusion of physics, what other incredible physical phenomena are hiding right in plain sight, just waiting for us to understand them?